4 damaging mechanisms in stress 21 chromium, 1 nickel ferritic austenitic stainless steel have been analyzed. Duplex stainless steels are characterized by high mechanical properties with corrosion resistance in various aggressive environments, competitive production cost. Traditional application can be found, for example, in chemical industries, petrochemical industries, nuclear industries. The two-phase structure of ferrite and austenite forms duplex stainless steel. The following figure shows a typical microstructure of the duplex stainless steel. The duplex microstructure is most often in a metastable state, preserved by fast cooling after solution heat treatment at a temperature above 1030 degrees. This heat treatment and after fast cooling after solution treatment should be properly handled to be in order to avoid the decomposition of the original microstructure and the precipitation of secondary phases, often deteriorating the corrosion resistance and the toughness properties. With respect to precipitation of secondary phases, there are three different temperature ranges. With respect to mechanical properties, the important characteristics of the duplex stainless steel is their extremely high proof strength at room temperature, twice that of comparable austenitic grades, and the high proof and tensile strength are the result of several simultaneous mechanisms. The following figure shows the different sigma epsilon diagram of different kinds of stainless steels. Chemical composition of the main types of duplex stainless steels is given in the following table with the yield strength values. The yield strength of the duplex stainless steel sigma epsilon isn't clear identifiable. By convention, it is possible to assume the yield point as value corresponding to 0.2% deformation. In this work, 21 chromium 1 nickel duplex stainless steel has been analyzed. It's a steel which offers high mechanical properties and good corrosion resistance, and approximately equal amounts of austenite and ferrite forms 21 chromium 1 nickel duplex stainless steel microstructure obtained after solution heat treatment at 1050 degrees for 1 hour. The chemical composition of this material is given in the following table. The aim of this work is the investigation of the damaging micromechanisms in this material by means of tensile tests and scanning electron microscope observations. This figure shows the specimen's geometry, and the following table shows the dimensional characteristics of these specimens. In order to identify damaging micromechanism, it is necessary that specimen surfaces are metallographically prepared by means of electrochemical etching. With respect to light optical microscope, specimens were etched in aqueous solution of 17.5% sodium hydroxide with an applied potential of 50 volts for 30 seconds. With respect to scanning electron microscope, the specimens were etched in aqueous solution of 10% oxalic acid with an applied potential of 6 volts for 60 seconds. A macrotensile test was carried out by means of a tensile testing micro machine, which mainly consists of two parts, a clamp and a tensile holder, which consists of a servomotor pneumatic slide, linear variable differential transformer, pneumatic slide. During macrotensile test, 3 SEM observation points were identified in order to distinguish 3 different areas during macrotensile test. Tensile tests were performed under deformation control conditions. Specimen deformation were measured by means of linear variable differential transformer, and some observations were performed considering different magnifications. The following figures shows 21 chromium 1 nickel duplex stainless steel microstructure, which is constituted of austenitic islands, light gray, in a ferritic matrix, dark gray. Then some images obtained during microtensile tests are reported. It is possible to observe the deformation of the austenitic grains and the presence of slip bands, both in ferritic and austenitic grains, which start from low deformation conditions, and their density increases more and more, which deformation increases. Then it is possible to observe twinning in an austenitic phase. Other images obtained during microtensile tests at different magnifications are reported. It is possible to observe cross slips in austenitic grain and ferritic grain, and it is possible to observe phases debonding mechanism. Then the following figure shows very high stress pigment. Quantitative microscopic deformation analysis of ferritic and austenitic grains was performed by means of SEM observations during the development of tensile tests, focusing both longitudinal and transverse direction. The following figure shows the transverse microscopic deformation procedure. Before procedure with measures, the areas with the clear edges were identified. For each area of measurement, 2 reference extreme points were identified, and the distance between the 2 ends, the yellow line, was divided into 4 equally shares, where farthest measures were carried out. Then longitudinal microscopic deformation procedure is reported. Then transverse microscopic deformation analysis is reported. It is possible to observe that ferritic grains are characterized by higher transverse microscopic deformation.